Now we continue looking at diatomic molecules, molecules made of two atoms. You can look at this material in your textbook or in adjusted chapters from Gen Chem textbook. We already look at lithium and beryllium, so we'll go further to boron, carbon, nitrogen, oxygen, fluorine, and neon. They have 3, 4, 5, 6, 7, and 8 electrons and outer shell. So that's where we stopped. Beryllium has 2 electrons on 2s orbital and none at 2p orbital. So there are 3 empty 2p orbitals. When we go to the next element, boron, we can start occupying 2p orbitals. So how 2p orbitals can interact? 2p and 3p orbitals have that shape, just a reminder. 2 nodes, positive, negative, positive, negative, positive, negative, and there is nodal plane coming through the atom. Atom is located here and there. Outer shape of 3p and 2p is very similar. You can look at orbitals in this way. So one orbital will go along y-axis, one along z-axis, another is along x-axis. So all 3 of them are perpendicular to each other. They can form different bonds. If 2p orbitals will overlap with positive nodes, so they will have common area here. You'll have constructive interference, and they will make sigma bonding orbital. So there are nodes here, node there, but there is overlapping area in the middle. Alternatively, orbitals that are perpendicular to the bond direction can overlap plus to plus, minus to minus, and these are atoms having node between them. These are pi bonding orbital. There are 2 of them. One is perpendicular to another. So when you have 3 p orbitals, you can make 1 sigma bond and 2 pi bonds. As a result, when we have atoms of second period starting from boron and ending at fluorine, we have overlap of 2s orbitals forming 2s sigma bonding orbital and anti-bonding orbital. Now 3p orbitals from each side gives us 2 pi bonding and 1 sigma bonding orbital. Which is higher, which is lower, depends on atom. Now we have anti-bonding pi orbitals and anti-bonding sigma orbitals as well. So you remember at each orbital we can put 2 electrons. Then we can start filling them. For example, for nitrogen. Nitrogen is number 7, so it has electrons at 1s level. 2 coming from one, 2 from another. All these are occupied, but overlap of 1s orbital is very small. 1s is core, and they are very close to nucleus. As a result, you can see the difference between these 2 numbers is practically non-existent. These orbitals play no role in chemistry, and the energy is very low. Now, the real chemistry starts with 2s orbitals. 2s orbitals overlap, making bonding orbital, and two other electrons occupy anti-bonding orbital. So total bond order from this will be 0 again. Next, we have sigma bonding orbital having this shape. So good area between and two nodes around. Next, we have two of pi bonding orbitals, a sausage above, a sausage below, and two atoms in between, and another is perpendicular to this. Unoccupied are pi antibonding orbitals. You have a node between them and node in this direction. As a result, when we put all our atoms, 2 on bonding, 2 on antibonding, 2 on bonding, 2 on antibonding, total bond order is 0, then one pair here, one pair there, one pair there. 3 pairs of bonding electrons make triple bond. Bond order is 3 for nitrogen. We can look at other elements of this earth. As we have seen for lithium, we have bond order 1 and weakly bounded molecule. Beryllium bond order is 0, again as we have seen, one pair on bonding, one on anti-bonding. This molecule does not exist. B2 theoretically can exist having one pair on bonding, one on anti-bonding, and 2 electrons on bonding orbitals. So the molecule will be paramagnetic and total bond order will be 1. Next, C2 molecule can exist in gas phase, has 2 pairs of electron on bonding orbitals and bond order is 2. We already seen nitrogen with bond order 3. And next it will be oxygen that has 2 electrons on 2 separate anti-bonding orbitals. So the molecule will be paramagnetic and bond order will be 2. 3 electrons on bonding, 3 pair electrons on bonding and 2 electrons of anti-bonding, making 2. Fluorine has 2 pairs of anti-bonding and 3 pairs of bonding p orbitals, so total bond order is 1. Now let's look at carbon monoxide. There are 2 different atoms here, carbon and oxygen, and oxygen is more electronegative and its orbitals has lower energy. Oxygen has 6 valence electrons and carbon has 4. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So total number of electrons will be 10. As a result, we are filling the orbital same way as before. 1 pair on bonding orbital, 1 pair of anti-bonding, and then 3 pairs on bonding orbitals, sigma p and 2 pi p orbitals. Total bond order is 3. Electrons are closer to oxygen, so molecule will be polar with more negative oxygen and more positive carbon. Now let's look how they will look like. So carbon, oxygen are connected. to each other. Overall shape of molecule will look like this. Carbon is bigger than oxygen. Now orbitals will be highest occupied will be sigma 2p orbital. You see carbon, oxygen, and its overlapping area here, and a large orbit electron cloud around carbon atom. Oxygen is much smaller. Now there are two identical pi orbitals here and there, perpendicular to each other. And then there is antibonding sigma 2s orbital, slightly asymmetric because carbon is not oxygen, and bonding sigma 2s orbital, again asymmetric, shifted towards oxygen. There are also unoccupied orbitals of carbon monoxide, like here. They are all identical, two of them, and they have one node here and one node there. Node, remind, is area with zero electron density. So you have positive, negative area here, and this molecule additionally can make chemical bond to something else. That's why carbon monoxide is reactive. It's visible that oxygen atom is smaller than carbon atom. Again,